Exercise 7.8 notes, exponential models with differential equations. So first we're going to talk about the exponential growth and decay function, y is equal to a times b to the t power. So this should look familiar from Algebra 2 when you learned about the exponential equation. Just recall that this a represents the initial value and b represents whether it's a growth or decay. And what's important here is not necessarily that parent function for the exponential, but what is important is when we take the derivative, so using it as a differential equation. So when we derive this, this is dy dt is equal to a times b to the t power times natural log of b. Okay, remember this is because when we derive a to the t power, or I believe it was in the notes prior, a to the x power, okay, this is equal to a to the x times natural log of a, whatever that base is. Well, from here, we know that a times b to the t power is y. So this is dy dt is equal to y times the natural log of b. Natural log of b is just a number, so we can go ahead and call that k a constant. So this is equal to k times y. Again, this is a number, which we're just going to call k. So if k is greater than 0, we know that we have a growth. In other words, if we have a positive exponent, we have a growth. If k is less than 0, we have a decay. If we have a negative exponent, then we have a decay. So it says the rate of change of a quantity is proportional to the size of the quantity. So anytime you see quantity, that is just talking about the y value, okay, or whatever value correlates to the problem. So it might not always be y. We could use the variable w, the variable p, etc. So number 1 says, set up a differential equation for each scenario. It says the weight of an animal is increasing at a rate proportional to its weight. So a weight of an animal increasing at a rate. So we know that's dw dt. Proportional to its weight, so we know we're using the constant k times a quantity. So this is going to be k times w for weight. And number 2 says a bacteria population is shrinking at a rate proportional to its population size. So we're going to have dp dt, so p for population this time, is equal to k times p. Okay, then it says, let's say we take dy dt equals ky and use separation of variables to find a solution. So remember, separation of variables means we have to get the variable on the same side. So I'm going to end up moving dt with the k and y with the dy. So this becomes 1 over y dy is equal to k dt. Take the integral of both sides, and we get natural log of absolute value of y is equal to k times t plus some combined c. So remember before we said one side would give us plus c1, the other side would give us plus c2. We combine them all on one side, we have a combined c value. Okay, then in order to get rid of the natural log, we're going to take the exponential of both sides. So that leaves us with y is equal to e times kt plus c, which is equal to e to the kt times e to the c, which gives us c times e to the kt, because e to the c is just some value, right? It's a number, so I could just create that as a constant and put it in front of the exponential function, okay? So this right here is actually going to represent our solution to the differential equation, where c is going to represent some initial value. So what's awesome about this equation is now when we are met with other types of differential equations of dy dt equals ky, we don't need to integrate it every single time. Instead, we can use that solution to find the particular solutions to other differential equations of the same type. So number 3 says dy dt is equal to 6y and y is equal to 5 when t is equal to 0. So dy dt equals to 6y. Well, that 6 is the same as saying k, because remember our equation is dy dt is equal to k times y. And then y is equal to 5 is our c value, because that's our initial condition. How do I know it's our initial condition? Because t is equal to 0. So I can write that as y is equal to 5 times e to the power of 6t, and that would be my particular solution to that differential equation. Same with number 4, I would get y is equal to 4 times e to the negative 3t. Okay, again, because negative 3 is my k value and 4 is my c value. Okay, number 5 is how you would see it most likely on an AP exam, and I would say multiple choice. I don't believe there's very many instances where you would see this as an FRQ. And then overall, on the BC portion of the AP exam, this is only accounted for 3% out of the 7% for differential equations. So it's a very small part of the test. So number 5 says an animal weighs 3 pounds at birth. So that is our initial condition C. And 4 pounds just 3 months later. Oh, this is extra information. The weight of the animal is increasing at a rate proportional to its weight. Well, we know we can write that as dw dt is equal to kw. Set up a differential equation for this scenario. How much will the animal weigh when it is 5 months? So notice when we set up the proportion for that differential equation, we know that we can write the solution to be w is equal to 3, okay, the initial value, times e to the kt, and then use that extra information it gave us to find k. So 4 pounds would be w, so 4 is equal to 3 times e to the k, and then time is 3 months, so times 3. You would then use Desmos or any type of calculator to simplify this. So if you're using Desmos, you would type in 4 tilde 3 e to the x sub 1 times 3, and this should give you a value of 0.09589 ... because it's a very long decimal. And what this gives you is k, so k is actually equal to that value. Well, now we know that k is that value. I can plug in that k value to my solution, which is w is equal to 3 times e to the power of 0.09589 t, and then use that solution, that particular solution, to find my answer of how much the animal will weigh at 5 months by plugging in 5 for t. So w is equal to 3 times e to the 0.09589 times 5. Plug that into Desmos, and I get w is 4.845 pounds, and that is my answer. Okay. At the top here, it talks about the growth and decay model and how that correlates with the exponent. And remember, that is because of the k value. If k is greater than 0, it is positive, so it's a growth model. If k is less than 0, it's negative, so it's a decay model. So another type of AP question, again, most likely multiple choice, would be one talking about doubling time or half-life. So it says a population y grows according to the equation dy dt, so dy dt is equal to ky, where k is a constant and t is measured in years. If the population doubles every year, what is the value of k? So we know that the solution to this is y is equal to c times e to the kt. Okay. And for here, we also need to know that if we are finding that initial condition value, that constant, if we talk about the beginning of time, so when t is equal to 0 years, we could say when t is equal to 0, this implies our y value has to be equal to 1. Because if you plug in 0 right here, e to the 0 is 1. And 1 times c, since we don't know what c is, let's just call it 1. Okay, what this gives you is a y naught value or a initial condition. Okay, so if I was to write this, this would be y times our initial condition 1 is equal to our initial condition 1 times e to the kt. And then I would plug in the information they gave us, and it says doubles. So we know our y is going to be 2. So 2 times 1 is equal to 1 times e to the k. And then it says every 7 years, so that's going to be 7. Okay. And then I just solve for k, again using Desmos, and I get k is approximately 0.099, which is what it was asking for. So every single type of doubling time problem is going to be set up in this exact same way. The only value that you end up changing is the time value t. If you're given a half-life type problem, you would just replace this 2 with a 1/2 and then again solve exactly the same.